We're now going to start a segment on non-bipartite matching, and we'll see some exciting results in the next sequence of lectures, both in terms of algorithms and also in terms of characterizations of the polytope that is the polytope of matchings. And this is similar in spirit, though more difficult to obtain, of the results that we saw for the matching polytope and the polytope of perfect matchings for bipartite graphs. Before we jump into understanding the polytope, this will be that will be the topic of future lectures. We're going to give a characterization of a maximum size matching. And just because we're going to be saying this, we're going to be using these words a lot, I just want to make sure we're crystal clear on the difference between maximal and maximum or maximum size. And this is important not just for matchings, but just in general. So a maximal matching, a maximal independent set, maximal subset subject to some constraints, is one where you cannot grow it in any way. And this and these do not have to be the same, and this doesn't have to be at the largest possible size. Now, in contrast, a maximum matching or a maximum size matching is even less ambiguous, is one which is surely maximal, but in addition to being maximal, it can't be increased at all. I'm sorry, it is maximum size compared to any other matching. And so we are going to be talking about maximum matchings here. So let me first give a definition of an M-Augmenting path, and it's easiest to do this just giving an example. So here is a very simple graph, and I will choose so the squiggly line is a matching, and you can see that it's a maximal matching because there's no edge I can add to it in order to increase it. But it is not maximum because choosing a different color now, these two edges form a maximal and maximum size matching for this very simple graph. Now this graph is very simple, but it illustrates the core of what this lecture is going to say, and that is that basically, if you have a matching which is not maximum size, then you can always find an augmenting path that finds a larger size matching. What is an augmenting path? It is a path that alternates between edges not in the matching and in the matching. And it's called an M-Augmenting path because it's in reference to what the specific matching that we have is. So an M-Augmenting path is a path v1, v2, v3, v4, v2k, so you can see that it has to have an even number of vertices. So what this means here is that the edges are v1, v2, and v2, v3, etc. v2k minus 1 to v2k. And as with this example, an augmenting path is one that has an odd number of edges and therefore an even number of vertices, where the first edge is not in M, and the second edge is in M, and we proceed as follows. And because we have an odd number of edges, because of the even number of vertices, we're going to end up with something that is not in M. And what is straightforward to see, is that if we can find an augmenting path, then in fact then M must not be optimal. What's important is that the converse is also true, and this is a characterization of maximum matching. So I'm going to write this as a theorem because it's an important result. M is a maximum or maximum size matching. Sometimes I may get lazy and just write max matching, but I mean maximum size, not maximal. If and only if there does not exist an M augmenting path. So let's prove this. So one direction is obvious. So let's call the direction that M is a maximum matching implies that there doesn't exist an M augmenting path. This is obvious just by virtue of the fact that we have an M augmenting path. But again, let me perhaps put this as an exercise, because what you need to do just to complete all of the details is to show that if you have any matching and someone produces an M augmenting path, then by doing what's illustrated in this figure, basically swapping the edges in and out, you're left with a matching of size at least one more. But we need to just check that I can put in these other edges. I can do this swap without leading to any violations. So I need to make sure when I do this that, for example, there was no edge that looked like this. If I did that, then I would have to then I wouldn't gain anything by swapping. Right? In fact, I wouldn't be able to swap just these edges. Yeah, so you can see that it takes a little bit of care just to make sure that this is true. But this is the easier direction. So we're going to focus on the other way. So let's prove this direction. In other words, we're going to show that if M is not, I'm going to show the contrapositive, is not maximum size, then I can find an augmenting path. An M augmenting path. And this is the statement that we need to show. Okay, so if M is not max size, then there is some other matching that is a bigger size. So then there exists, let me call that M dash, that's a matching. And M dash is going to be at least one bigger than M. So again, a matching is a subset of edges. Though we're going to be talking about the nodes or vertices that are covered or not covered by a matching, but a matching is a subset of the edges. All right, so now let's make a graph. Let's let G hat be the graph with the same vertices, V, as the original graph, and edges, all the edges that are either in M or M dash. Now note that M and M dash are allowed to have common edges. There's nothing forbidding that. Okay, so let's think about what is G hat. So G hat is a matching. I'm sorry, G hat, its edges are a union of matchings. And therefore, note that the degree of each vertex in G is at most 2. And so this is clear because for any vertex, it can only have one edge. It can have an edge from nothing. It could be an isolated vertex. It could have an edge from M or M dash, or it could at most have an edge from M and M dash, but it couldn't have any other edges Because if it had any other edges, it would have to. It wouldn't be a matching. Okay. So so what does that mean? If G, if everything in G has degree at most 2, then what does G look like? Well, that means that G hat is a union of isolated nodes, paths, and circuits. So now let's see which let's see what happens from, let's use the assumption that M dash has size at least 1 more than M. Now you can see that we're just going to count edges, and there's at least 1 more edge in M dash. In any cycle must be even length, because otherwise you'd have a violation. Otherwise you would start and end with an edge of either M or M dash. So any cycle, if I delete all the cycles, I've deleted the same number of edges from M and M dash. And similarly, there's no edges in an isolated node. So now if I look at all the paths could be even length or odd length. And again, by the same reasoning, if all the paths were even length, then I wouldn't be able to have 1 more edge at least in M dash than M. So basically, because M dash is bigger than M, there must exist a path of odd length. Let me specify odd number of edges that starts and ends with an edge of M dash and alternates M dash M, M dash M. This is an augmenting path. And this is exactly what we wanted to prove. This proof is interesting because it not only tells us that we can increase, not only characterizes augmenting paths, but it also tells us how we can move from one matching to another, basically by looking at these augmenting paths that use an edge from one matching, an edge from another, an edge from one matching and another. And this by itself is going to be is useful in other contexts as well. But it's nice to have this this characterization. So this suggests a natural algorithm for finding a maximum matching. Just start throwing edges in. It basically tells you that you can't go wrong in a way. You start adding edges until you can't add any more edges, and then and then you start searching for augmenting paths. So what we're going to see is that this is a great idea, and this is a good basis, a good starting point for finding maximum matchings. But it's non-trivial for a non-bipartite graph. So let's first see why it is easy for a bipartite graph to use this basic idea. So let's let G be a bipartite graph. So that means that V can be split into red and blue nodes. So let me just call it U and W. And given a matching that may not be maximum size, just any matching M, I'm going to choose an orientation of the edges of G. Sorry, what I meant here is that it's the union. Right, so this is the disjoint union of U and W. Think about U as being the nodes on the left, W as being the nodes on the right. So given a matching M, let's orient the edges E as follows. The edges in E. So take any E that's equal to UW and orient E equals UW from U to W if E is not in the matching, and orient it from W to U if E is in the matching. So that means that we have our bipartite graph here. We have some edges that are in the matching, and we have some edges that are not in the matching. And you can see that in this example, I can't add any more edges into the matching. So and so what is my orientation here? The squiggly lines again are the ones in the matching. So if it is in the matching, I orient them this way, and if they're not in the matching, I orient them this way, and you can see what's about to happen here. So let's let UM be a subset of U and WM be a subset of W. These are not subsets of nodes. Let this be the set of nodes that are not covered by the matchings, by the matching. So let UM and WM be the nodes in U and W respectively, not covered by M. So what's what's not covered on the this is U, this is W. This is not covered because there's no edge of the matching that's incident upon that node, and on the right this is not covered. And so it's straightforward to see that there exists an M-Augmenting path if and only if there exists a directed path from UM to WM. This is a particularly simple example that I've given you, and you can see it, but you can check this. So I'll leave this as an exercise. But once you convince yourselves of that, then if it exists, this is now in the realm of problems that we have looked at before. We've looked at shortest path, etc. So if it exists, this can be found efficiently. So for a directed path, for a bipartite graph, we can use this characterization of optimality in a very straightforward way, using these two color classes. We also have a nice characterization of when a bipartite graph has a matching that covers all of the nodes on one of the two color classes. And of course, that's the largest that it could possibly be. This is called a perfect matching if the color classes are balanced. So here's the result. A graph G, which is bipartite, with color classes, again, U and W. Then G has a matching covering entirely one of the two color classes, say U, has a matching covering U, if and only if the cardinality of the neighborhood of a set S is bigger than S for every S that's a subset of U. So again, N of S, so if S is a subset of U, then N of S is a subset of W, and it is all the neighboring nodes of S. And what it's really saying is that you can just check locally. So if you have any situation like this, then what this result is saying is that there can't be a perfect matching because you have a bottleneck here. So it's expressing the failure to have a perfect matching essentially in terms of a local bottleneck. It's saying that you have to have a non-contraction of any subset. So let's quickly prove it. One direction, of course, is clear. So this direction is obvious. Namely, if G has a perfect matching covering U, then we can't have any. We can't have n of S, the cardinality of that being strictly less than S. And just for the proof, look at whatever the maximum matching is, and the maximum matching, the size of n of S has to be at least the size of S. So let's look at the reverse direction, and this will give us an opportunity to use a result from a previous lecture on bipartite graph, and something that we proved twice, in fact, and once using the integrality of the bipartite polytope, which we got from total unimodularity. But we had also proven this more directly before we introduced total unimodularity, but again, relying on these integrality ideas. So what does Koenig's theorem say? Koenig's theorem, recall, tells us that for any bipartite graph, sorry, squeeze that in there. For any bipartite graph, the size of a max matching is the size of a min vertex cover. Size of max matching is equal to the size of the min vertex cover. Remember, we used duality for this. So it's enough to show that each vertex cover C has cardinality bigger than or equal to U. So is that so hopefully this is clear. Think about why it's enough to show this. So so now where do we go from here? So now, what are the neighbors of what's in U but not in the vertex cover? Remember, the vertex cover is a subset of the nodes. So first, we observe that this has to be a subset of C intersect W. Remember, we have, again, our picture here. This is U on the left, and this is W. I'm not making an assumption of whether they're balanced. So what I'm saying is that the neighbors of what's on the left minus what's in the vertex cover is something that's in the vertex cover on the right, simply because a vertex cover has to cover every single edge. So if you have something here that's not in the vertex cover, it means that it must be connected to an edge that belongs to the vertex cover on the right. So what this tells us is that C is equal to C in U plus C in W. Okay, this is just because U and W are disjoint. And then by the above containment, this has to be greater than or equal to the cardinality of C in U and the cardinality of the neighbors of U minus C, again, directly from the cardinality above. And this, in turn, is greater than or equal to C, the cardinality of C in U, plus the cardinality of W minus C. Oh, I'm sorry, of U minus C. Now, where did this come from? Let's look back. This is basically my assumption. Right, so this is what I'm trying to prove. My assumption is that the size of neighbors is greater than or equal to the set that you started. So I just replace the size of the neighbors by something that's potentially smaller, the size, the set at where I started. So this is by assumption, by the assumption. And this is equal to u. So this concludes this result. So we've done three things in this lecture. First, we have a characterization of maximum size matchings. A matching is maximum if you can't find an M-Augmenting path, and that's a characterization of maximum size. Then we showed that we can use that directly to come up with an algorithm based on our ability to find paths in a directed graph efficiently for bipartite graphs, and we use the bipartiteness in an important way. And then finally, we have this characterization of when G has a perfect matching. I'm calling it perfect because it covers all of one color class. And again, if it's balanced, then every edge, but then by definition, it would have to cover every single edge. So we're not going to use these ideas, or in particular the first idea, that characterization, to talk about non-bipartite graphs. And the important part to note is that we didn't use bipartiteness at all in this characterization of a maximum matching. So this is what we're going to turn to next.